Hey everyone, it's time for a new project. If you haven't figured it out already, I want to create an active suspension system for a radio-controlled car. I had high hopes of trying to attempt this with the RC Streamliner, but I think it's better to start with something a little bit larger that I can fit the electronics in more easily. Of course, I'd love to try this on a full-size car, but I think it's going to be much safer and cheaper to try this on an RC car. So I've drafted this antique radio-controlled truck into service for building an active suspension. I don't necessarily want to cut this truck up, so my goal is to try to make everything on this truck reversible. So before I launch into this, I think it makes sense to just do a quick introduction to active suspensions. This is a complex topic to cover, but I'll do my best to break it up along the way and focus on areas relevant to this project and do my best to link to additional reading material. So the cool thing is active suspensions are a really hot topic right now in the automotive world. So there's a dearth of great articles out there on the different types and means of controlling active suspensions. Almost all of the so-called active suspension systems on production cars today are actually considered semi-active suspensions. The simple way I differentiate a semi-active suspension from an active suspension is that a semi-active suspension cannot add energy to the system. That means that a semi-active suspension can only vary how much a damper resists movement. There are three main types of semi-active suspensions. The first one is a physically controlled valve or valves that can vary the dampening based on the road conditions. But due to their size and complexity, I didn't feel that this would be a easy fit into an RC car. The second type of semi-active suspension is the magnetorheological damper. Essentially, these are dampers filled with an oil with suspended ferrous nanoparticles. The damper has one or more electric coils around the valve or the piston, and the magnetic field from these coils can actually cause the mag fluid to react and thicken and actually control how much it blocks the valve's passage. So these are very fast reacting, being able to change dampening characteristics within a few milliseconds. It's something to explore in the future, and I think it's possible for a radio control car, but it's hard to find the right type of MR fluid for shock absorbers. The last type of semi-reactive suspension is the electromagnetic damper. And this is where the dampers are a type of linear DC motor, and the coils are linked to an external resistance circuit that can essentially vary the dampening based on the resistance. I'm not aware of anyone yet using this in a production car, but in theory they would be very fast reacting solution. This is totally possible for an RC car, but everything would have to be built from scratch. So on to active suspensions. Active suspensions can actually add energy to the system, meaning they have an actuator that can actively raise or lower the suspension and actively counteract forces like body roll. For this project, I explored a variety of approaches to creating an active suspension system. I looked at pneumatic active suspensions, but unfortunately these are typically a slower acting type of active suspension and less precise than other control methods, and primarily used for like load leveling in trucks. If you go and look at past Formula One cars of the early 90s, that they used hydraulic actuators for their active suspensions with very small precision controlled servo valves from the aerospace industry. Hydraulics would be really cool for this model, and I went so far as to design some pumps and valves. But ultimately, I just arrived at the conclusion that this was going to be a very heavy solution and massive and expensive undertaking with no guaranteed results. So I went ahead and shelved that idea. The last way of actuating an active suspension is electronically. If you were a child of the 90s, you most likely remember the Bose LS400. This used a linear DC motor similar to the voice coil of a speaker, which was able to actively control every aspect of the suspension extremely quickly. There were no conventional dampers, and the suspension was directly connected to the actuator. It's a really cool system, and I think it could definitely be replicated on an RC car type scale, but it's definitely not an entry-level active suspension project at all. So I looked at ways to create actuators from a cheap radio control car servo. Initially, my plan was to directly actuate the control arm with the servo with no conventional damper or spring. But after some research, I found this just wasn't an optimal solution. Before we go any further, we need to talk a bit about suspension dynamics. For this discussion, I'm going to assume everyone here is generally familiar with how dampers work and the basic concepts of compression and rebound. Stepping into this, the first concept is sprung versus unsprung mass. So sprung mass is essentially everything that the suspension is actually holding up, the body, the chassis, so essentially this middle part of the RC car. The unsprung mass is everything that is not held up by the suspension, such as the springs themselves, the control arms, the brakes, the wheels, the steering knuckles, the actual tie rods themselves. All of that compromises the unsprung mass of the suspension. Compression is typically said to primarily control the dampening of the sprung mass, and rebound, which is the return, actually controls the dampening of the unsprung mass. The goal of a damper in general is to tune out the frequencies of the car's sprung and unsprung masses as they encounter various surface conditions. Here are some example frequencies from one of the best articles written about suspensions from Kaz Technologies that I'll link to below, and it's a definite must read. Most of the papers online that I was able to find on this subject of active suspensions focused on the ride comfort of the occupants. Not something I really cared about too much. But I did find a few random anecdotal comments mentioning that the maximum performance is actually achieved by dampening the natural frequencies of the unsprung mass and in the wheel hop range of 3 to 4 hertz, which maximizes the time that the tire is in contact with the road. As you can see in a full-size car, that the natural frequency of the unsprung mass is somewhere between 15 and 27 hertz. Now, I have no idea what the natural frequency of my RC car unsprung mass is, but I wouldn't doubt, due to its relative size, that this would be a much higher number. So when I started looking at servos and their speed of movement, I couldn't find anything reasonably priced that would come close to dampening 15 to 27 hertz. At best, I was going to achieve less than 10 hertz for an active suspension response. So I went back to the internet and found most active suspensions actually utilize a softer inline damper and spring setup, which effectively dampens these higher frequency oscillations. So I opted to use this approach and actually use the servo actuator to control low frequency oscillations. And this design would also prevent any shock loads from damaging the servo. And being an off-road radio controlled truck, the dampers and the springs were already quite soft. So I think this works out really great. The active suspension should be able to take out the normal twist and roll that this type of car has naturally. Again, I only have the rear suspension mocked up right now because I only have just the one servo, and I'm still fighting with the design that will work for the front end. As I mentioned, the actuator is a 20 kilogram servo, which is hooked up to a rod, which goes over to a rocker with an arm ratio of roughly 1.2 to 1. The rocker is then hooked up to the coil-over spring and damper. The end of the rocker arm can travel roughly 20 millimeters vertically, and the wheel ratio, the ratio between where the shock actually meets the control arm and the pivot point of the full length of the control arm is roughly 2 to 1. So that means that the servo can essentially control 40 millimeters of travel at the wheel. I have no idea, of course, what the ideal amount of travel should be, but this is a large safety margin that has been built in to protect the servos. I can modify this very easily. Now, of that 20 millimeter vertical travel at the rocker, roughly 5 millimeters of that travel is a preload travel. So that means if the car is sitting level like this, the servo can go ahead and add 5 millimeters of preload to the spring on the coilover, which would be used to help keep the car level when turning, or for improved weight transfer when there's not a significant bump load already on the car. Again, this is just a guess. We'll find out more through testing whether or not this is the right amount. So now onto the actual sensors that we need for this project. I'll cover this more in a later video, but all of the active suspension control schemes need to know the relative velocities of the sprung and unsprung masses. So this truck will use an MPU 6050, which is just a cheap 6-axis gyro accelerometer that will be located in the middle of the truck, which allows me to measure the velocity of the sprung mass. And then to measure the velocity of the unsprung mass, at each wheel there is a 10K potentiometer with an arm that is hooked to a tie rod on the suspension. And essentially what this does is, as the control arm deflects, I will get different readings through the potentiometer so that I will know what the velocity of the unsprung mass at the end of the control arm is. Now, once I get in all the servos and get it all hooked up, I'm planning to wire this all to a tried and true ESP32, primarily so I can wirelessly stream data off the truck while it's running, because that's going to make it a lot easier. The controller is going to be more complex than anything I've done before, and all the papers I've been able to find focus really on simulating a quarter model of the car, meaning that they just simulate a single wheel and its suspension. So I thought about building a test rig similar to what I've seen in these papers, but I just didn't want to go through the time of building a one-off test rig. So I'm going to go ahead and try to make a shaker rig that initially will be just for a single wheel, with a motor and an eccentric that allows me to vary the frequency and test different control schemes. Eventually I'll probably need a 4-wheel shaker rig so that I can actually see the data off of all 4 wheels at once and optimize it from there. I also need to work out the frame of reference for the accelerometer, which is affected by all 4 wheels. In the papers this was easy because the accelerometer is put directly on top of the sprung mass, which was suspended directly over the wheel. So no math was required to be worked out really. I'm not sure if I can use the vertical displacement directly from the accelerometer, since it'll be mounted in the center of the chassis, or if I will need to work out a relative z velocity vector in relation to the absolute level from the gyro data, or I might even possibly need to come up with some component vectors for each of the sprung masses for each of the wheels. I'm not sure. If you all have any ideas, let me know what you think. Thanks for sticking through this. I know that was a lot of technical information for just one video, but I really wanted to kind of set the base of where the development's going to go from here. And unfortunately, active suspensions really require some grounding in the basic concepts of suspension design, and ultimately we'll get more into control strategies. Actually, probably more than anyone wants to get into control strategies, so we can talk about how this active suspension would actually be implemented. So thanks for watching, and stay safe out there.